So, the moment you've all been waiting for, the review for this upcoming exam. So, here I actually already wrote down all the expressions for Chapter 12. Just make it a little bit quicker, and then I'll erase these, and then we'll do the ones for Chapter 13. Also, as we're going through, I'll point out two of the long problems, since two of the long problems will come from this chapter. So first off, we have the center mass position. So center mass position then is equal to the sum over the mass times the radius. This is away from wherever my chosen origin is, all divided by the total mass. Now again, in Cartesian coordinates, this thing simply breaks up into different directions. So I'll have one for x center mass, y center mass, and z center mass. So in this case, I just replace this with xi, yi, or zi. We have the moment of inertia. This thing is defined as the sum over the mass times the radius squared. This is only for discrete objects. If I have continuous objects, I'd have to actually do an integral. But again, on this exam, during the regular portion of the exam, there is no integrals. Wink, wink. That's not necessarily true for the extra credit. And we'll go through that a little bit, but for now, since this is true for the regular exam, I'm not going to bother writing down the integral version, because as you see, I have no room. Anyways, I mostly read this down because, again, this shows that the moment of inertia is additive. So if I have multiple things all creating the object, and then the total moment of inertia is simply the sum over all the moments of inertia. Again, I will give you moments of inertia for the objects. I'm not going to expect you to integrate over them. And I'll have that on the front page, so don't waste any space with different moments of inertia. That'll be there. But one thing that will be useful is the parallel axis theorem. So this says that the moment of inertia about some point P is equal to the moment of inertia about the center of mass, plus the mass of the object, so this thing has a mass of m, times the distance d, where the distance d is the distance from the pivot point to the center of mass quantity squared. Now over here we have rotational kinetic energy. That's equal to 1/2 the moment of inertia about whatever the pivot point is, times the angular velocity squared. Then we have rolling without slipping. Again, this is when an object has translational velocity as well as rotational velocity, like a wheel in a car or a bicycle or a rollerblade or something. That's all kind of going in the same direction. This is equal to, so the total kinetic energy is the rotational kinetic energy about the center of mass, plus the translational kinetic energy of the center of mass, which means that this is 1/2 the moment of inertia about the center of mass times the angular velocity squared, plus 1/2 the mass times the center mass velocity squared. Again, omega is related to the center of mass velocity, so if I replace that, this is the same thing as 1/2 times the moment of inertia about the center mass divided by the radius squared, plus the mass, and all of that's times the center mass velocity squared. So from here we can get work. So work then is equal to the torque times the change in angle. Again, this is only true if the torque is equal to a constant, which it may not be, which is also equal to the change in rotational kinetic energy. And then the power is then equal to the torque times the angular velocity, and this is true for the average torque as well as the instantaneous torque, or instantaneous power. Again, here, if this is not constant, you would actually have to integrate, but again, we're not doing integrals, so I'm not going to bother writing that down. Torque, remind you, is equal to the cross product between the r vector, which is the r vector which points from the pivot point to the location of the force crossed by the force. So this magnitude then is equal to the, again, r vector, that's what you guys usually call moment arms, times the magnitude of the force times sine and angle between the two. So this means that the force points this way, r vector points this way, theta then is specifically that angle between the two. Newton's second law then says that the sum of the torques is equal to the moment of inertia times then the angular acceleration. Actually put a vector sign in there. Again, what we care about here is that counterclockwise rotations correspond to a positive torque. Clockwise rotations correspond to a negative torque. Finally, we have angular momentum. Angular momentum is defined as cross product between r. So r, again, is going to be the radial vector which points from the origin to the location of the momentum, crossed by the momentum, which means the magnitude is then equal to the magnitude of the radius times the magnitude of the momentum times sine and angle between the two. Technically, this is only true for point particles. Okay. So again, here, this is specifically the angle between these two vectors. So the momentum is this way, radial vector points this way, then that is theta, the angle between those two. Now it turns out that the time rate of change of the angular momentum is equal to the torque. So this is where torque actually comes from. Now if I have a rigid body, which is what this one is for, so this is for a rigid body. So again, a rigid body is anything that does not deform under rotations. So for example, a ruler, a disc, anything like that, that's actually rotating. The moment of inertia times the angular velocity then is equal to the moment of inertia. Or sorry, not the moment of inertia, the angular momentum. Again, the time rate of change in the angular momentum then is equal to the torque. This is technically the external torque. Now, if the external torque is equal to 0, this implies then that the time rate of change of the angular momentum must be equal to 0, which means the angular momentum must be constant, which means that the initial angular momentum must be equal to the final angular momentum, which is what we call conservation of angular momentum. There goes some old truck getting down the road. Anyways, so before we move on, let's point out questions that are going to happen. So here, one question for a long one is definitely going to involve torque. So basically, it's going to involve all this good stuff here. So this is going to be one question. So this will be one question where there'll be masses moving linearly as well as a pulley, which is, say, rotating. So here you're going to have to do the sum of the forces on anything that's moving linearly. So that's just Newton's second law. It's going back to chapter 2, or not chapter 2, exam 2 stuff. And then the pulley is going to rotate. So in that case, you're going to have then the sum of the torques. So this is long problem number 1. It's going to basically deal with all that good stuff. The second long problem is then going to involve, as I mentioned, some sort of collision, which means that it's going to involve conservation of angular momentum, which basically means it's going to involve all of this momentum stuff. But then after that, it's going to swing and it's going to move. So in that case, it's also going to involve rotational kinetic energy, i.e. conservation of energy, where in this case we then have to take into account that this thing is, say, going to swing. So in that case, has a rotational kinetic energy and then has a gravitational potential energy at the end. Now, this goes back to a question that Alec asked, over a week ago. But in that case, if I had, say, a piece of putty stuck on here, this is my rod, and the whole thing swings up. So in this case, notice that there's 2 different changes in gravitational potential. There's that of the putty down here, and there's also that of the center of mass of the rod. So I have to make sure I take both of those 2 things into account. So as far as the 2 long problems are concerned, these will be them. So first one is going to deal exclusively with torque, linear masses, so finding accelerations, things like that. So one thing to pay attention to when it comes to torque, how you know you have to use torque, is whenever you ask for an acceleration. So if I ask what is the acceleration of the system, or what is the angular acceleration of the pulley, something like that, automatically you know you can't use conservation of energy to determine an acceleration. You can only use that to find a change in height or a change in velocity. It has nothing to do with acceleration. So anytime I ask for an acceleration, i.e. angular acceleration or linear acceleration, I'm explicitly talking about torque. So in that case, look for that keyword, at least in that problem. It says find the acceleration. Automatically, you know you have to use torque. So here you're going to be dealing with something like a pulley, something like that. So this thing could show up in here as well. So parallel axis theorem, so that may or may not show up in this problem. And then here, so again, what will happen here is there'll be something colliding with something else. Now, you know you have to use moment of inertia instead of just, angular momentum instead of just linear momentum, because what will happen is you'll have some sort of rod, something like that, and then something hitting like it here. So this is the direction of momentum. So you know this has to be here because this thing is going to have a mass. This is also going to have a mass. So let's call this M1 and this M2. So because this thing is a rigid body, it has to have angular momentum as opposed to linear momentum. And again, this thing is going to swing. So what will happen is this thing's going to swing out. And what you're going to look for then is some sort of height. In that case, as I just mentioned, anytime you want to change a velocity or change in height, that just means conservation of energy, you don't have to use torque in this case. Plus torque would be complicated. Other things on here to note is that, center mass. This thing will have something to do with a short answer quick calculation problem. I'll tell you that. Rolling without slipping. So this will also be a short answer quick calculation problem. Now this could have easily involved in this, but again, we're trying to make this a little bit easier for you guys, so we're going to go with that. So good. So that's a couple of those. So good. So now we just have to talk about Chapter 13. So Chapter 13, again, is gravity. So Newton's universal law of gravity, primarily. Let's get rid of all this stuff. Take me an hour just to erase the board. Alright, great. Good enough. So, talk about Chapter 13. So, Chapter 13, first things first, is Newton's universal law of gravity. So this is that the magnitude of the gravitational force then is equal to G, which is Newton's constant, times m1 times m2 divided by r squared. So here, this is m1, this is m2, this is then r squared. So r squared, or sorry, that's r. So r is the center-to-center distance between these two objects. So center-to-center distance. The direction of the force is attractive. So that means this guy's going to be pulled in this direction. So it's going to be the force on 1 by 2. Simultaneously, this one's going to be pulled in this direction. So this will be the force on 2 by 1. If I have multiple point charges or point masses, let's say I want to know the force on the jth one, and this is equal to the sum over I of the Fji, which is the force on j by all the other i's, which means that this is equal to then G times mj, since mj is constant on all of them, it's going to get pulled out, times the sum then over I of mi over rij squared. Technically, this guy is negative in the rij direction. Where rij is just the force is directed along the line that connects these two, so it's just going to be in the direction. And again, it's negative because it's an attractive force. Now, again, technically this is only for discrete, meaning I just have a whole bunch of point masses everywhere. If I had a continuous body with a point mass, you would then have to turn this into an integral, but again, we're not doing integrals on the exam, at least not the regular exam, so we're not going to worry too much about that. At least for now. Good. So what else do we have to worry about? So we also have potential energy. So we know that the gravitational potential energy then is equal to minus Gm1 m2 over r. So again, m1, m2, r is the distance from the center to center of these guys. So this is the potential. From here, we can use conservation of energy again. One thing that is useful is what's called the escape velocity. So this is the square root of 2gm over r. So what this means then is if I had some massive body, let's say this is capital M, and I have a small object, little m, trying to move away from it, then escape velocity then is the amount of speed that it needs to make it out of the gravitational well of this guy and make it all the way to spatial infinity where this guy stops. So this is the escape velocity. We also have the orbital velocity. The orbital velocity is equal to the square root of g times m divided by r, where in this case, again, this is m, which is the mass of the body being orbited. Little m then is the mass of the body which is orbiting. This thing then has a tangential velocity, which is the orbital velocity. So this is how fast this guy is moving to keep it in orbit, i.e. so it doesn't crash into this central body. Good, so finally, the last thing we really have is what? Kepler's laws. Now again, Kepler's laws, the first two were basically more conceptual. So again, the first one just says that, anything orbits the sun in an elliptical fashion where the sun is at the foci of one of the foci at the ellipse. So that's more conceptual. Second one says that the area that's swept out in a given amount of time is always constant, so the area velocity. And the third one is what we care about, Kepler's third law. So the third law simply says that the period squared is equal to 4 times pi squared divided by g times the mass of the central body. So in this case, we're looking at him, times r cubed, where r cubed is the radius from the center of mass of the body which is being orbited to the center of mass. I have no idea what that was. Of the body which is orbiting it. So all this says is that the period squared is then equal to 4 pi squared divided by gm times the radius cubed. So basically, all of this stuff is going to pretty much show up on the long problem. So let's see here. So things that won't be on the long problem. So this stuff won't be in the long problem, but this will be in a short answer quick calculation. And then basically everything else here is going to be in the long problem. So the third long problem will basically be all of this stuff. This will be the third long problem. So okay, first long problem will deal with torques, as well as linear forces, so all that kind of good stuff. Second one will be conservation of angular momentum with conservation of energy. And then the third long problem is basically almost everything from gravity, except for the superposition. The superposition, though, will show up as a short answer calculation problem. Now, again, when it comes to the superposition, again, here what you're looking for are any types of symmetries. So definitely look for masses that have the same amount of mass at the same distance, because those forces are going to cancel with each other. So there's not going to be any net force for those things. So good. So the last thing are extra credits. So basically, the extra credits are all going to involve integrals. This is a beautiful time to have a long one. Close some of these windows. Hopefully that's a little better. So anyways, basically here, this is when we're looking at the integral versions. So again, the moment of inertia is going to be equal to the integral of r squared dm. The center of mass is another one. So r center of mass is going to be equal to the integral of r dm. What else is an integral? Also the gravitational force. So the magnitude of the gravitational force is then equal to g times the mass of the body which is feeling the force times the integral then of dm divided by r squared. So here you're chopping this thing up into a small dm, and then this is r, which is the distance to the little mass that you're feeling the force onto. Good. In all three of these cases, dm is the same. So dm is either equal to lambda dl. I think we're calling this eta. So this is eta dA, and then this is rho dv. So here, this is the mass per unit length times dl, where dl is the differential length. Eta then is the mass per unit area integrated over the area. And then finally, this is mass per unit volume integrated over the volume. Now again, typically we treat these things, lambda, eta, and rho, as constants, but they do not have to be. Actually, one of the homework questions deals with the fact that this is not. So these can actually be functions of position as well. So this can be a function of, say, x, if this thing is along the x-axis. This can be a function of x and y, and this can be a function of x, y, and z, or whatever coordinate system that you're looking at. But again, extra credit will involve something with an integral. So, I think that pretty much covers it. So we're going to have our Zoom meeting. You guys can ask me more questions about it then. Again, things to pay attention to. Don't worry about writing down all the different moments of inertia. I will give you those. You will have to know how to use the parallel axis theorem, though. So what else? So yeah, don't write down any of those moments of inertia. Again, I'll give you all the fundamental constants, so like G and all those different ones that we're going to run into. So little g, capital G, all of those different ones. Yeah, so same structure as before. 3 short answer, choose 2 of them. 3 longer problems, do all 3 of those, plus the extra credits. And again, we're going to give you more time. So in this case, you'll have an hour and a half to do the exam, plus take pictures of it, plus upload it. So ultimately, you'll have an hour and a half time frame to actually do all that. Again, we'll start at 9, so we'll have to have everything in by, say, 10:30. So when you go on there, there should be a separate submission for everything. So there'll be a submission for problem 1, submission for problem 2, submission for problem 3, submission for the short answer, submission for the extra credits, and for the group problems. So you upload all of those things basically individually. Yeah. So again, just take a picture of it, or if you have a scanner, go ahead and scan them. Either way is fine. It doesn't matter which way, whichever is more convenient, whichever is faster for you to do. So, since the first time we're doing it, we'll find out if that hour and a half is long enough. If not, we might have to adjust this for the next upcoming exam, and then for the final, just make sure we get everything done. But yeah, but while you guys are doing the exam, I will be available via email. So if you have a question, just email me, and I'll be sitting in front of my computer, I guess doing nothing else except for waiting for emails to see if you guys have any issues with anything. So yeah, otherwise I'll talk to you guys over Zoom, and we'll go from there.